Right. Let's talk about equations of linear motion. Now, these equations are also called kinematic equations of linear motion. In kinematics, we consider the motion of a body without taking into account the forces causing or affecting the motion. Secondly, as the name suggests, these equations only apply for bodies moving in a straight line. In such cases, the magnitude of distance and displacement is the same. Also, the magnitude of speed and velocity is the same. There is one more condition for these equations to apply. We know that the velocity of a moving body can vary uniformly or non-uniformly. For a body whose velocity varies uniformly, its acceleration is constant or uniform. But for a velocity that changes non-uniformly, the acceleration is not constant. Equations of linear motion only apply to uniformly accelerated motions. These equations tell us the relationship between displacement, velocity, acceleration, and time. There are three equations, so let's derive them one by one. The first one. Consider a body moving in a straight line such that its velocity changes from an initial velocity u at time t is equal to 0 seconds to a final velocity v at time t seconds. The acceleration of the body is equal to the gradient of the graph. This is given as v minus u over t. If we cross multiply, we shall have at is equal to v minus u. And if we rearrange, we shall have v is equal to u plus at. This is the first equation. The second one. Displacement s is given by average velocity times time. Average velocity is given as u plus v over 2. So for displacement, we multiply this by t. But equation 1 tells us that v is equal to u plus at. So if we substitute v in this equation, we shall have s is equal to u plus at over 2 times t. Opening the brackets, we have ut plus at squared, everything over 2. We can break this into two parts, so that we have 2ut over 2 plus at squared over 2. These two cancel out, and we shall have s is equal to ut plus a half at squared. This is the second equation. Alternatively, from this same motion, we know that the area under the graph up to the x-axis represents the total displacement. The shape is a combination of a rectangle A and a triangle B, so that displacement is equal to the area of A plus the area of B. Area of A is equal to length times width. The length is u and the width is t, so that we shall have u times t or ut. The area of B is a half base times height. The base is t and the height is the difference between u and v, or v minus u. So the area is a half times v minus u times t. So that the total displacement s is equal to ut plus a half times v minus u times t. From equation 1, v is equal to u plus at. We can rearrange it into at is equal to v minus u. Then we substitute this v minus u with at, so that we shall have s is equal to ut plus a half at times t. This will give us s is equal to ut plus a half at squared, the same equation. The last one. Displacement s is given by v plus u over 2 times t. And we also know that a acceleration is equal to v minus u over t. We can rearrange this part into t is equal to v minus u over a. And then we substitute this t u over a, so that we have s is equal to v plus u over 2 times v minus u over a. Now we do binomial expansion. For the numerators, v times v is v squared. Then v times minus u is minus uv. U times v is equal to uv. And u times minus u gives us minus u squared. For the denominator, 2 times a is equal to 2a. Minus uv plus uv is 0. So we remain with v squared minus u squared over 2a. And this is equal to s. If we cross multiply, we shall have 2as is equal to v squared minus u squared. And if we rearrange, we shall have v squared is equal to u squared plus 2as. And that is the third equation. And therefore, for a uniformly accelerated body, any of these three equations can be used depending on the missing quantity. Recall that deceleration or retardation is negative acceleration, and therefore the sign in all of these equations will change into a negative. Let's take a few examples. The first one. A car is moving at a uniform velocity of 27 meters per second. Brakes are applied and the car decelerates at negative 8.4 meters per second squared to a stop. How long does the car take to come to a stop? Now, what we do is gather what we know and what we need to find out. Then we choose the appropriate equation. The initial velocity u is 27 meters per second. The final velocity v is 0 meters per second because the car is coming to a stop. Acceleration is equal to negative 8.4 meters per second squared. We need t. So the first equation will apply. V is equal to u plus at. 0 is equal to 27 plus minus 8.4 times t. 0 is equal to 27 minus 8.4t. Minus 27 is equal to minus 8.4t. To remain with t, we divide both sides by minus 8.4, and we get 3.2 is equal to t, and therefore t is equal to 3.2 seconds. Another one. A car accelerates from rest at 5 meters per second squared. What is its velocity after 8 seconds? So the initial velocity u is 0 meters per second because the car is starting from rest. T is 8. A is 5. We want to find v. So v is equal to u plus at. That is equal to 0 plus 5 times 8, giving us 40 meters per second. Third example. A cyclist is riding at 15 meters per second. She sees a red light ahead and gently brakes over a distance of 50 meters to come to a complete stop. What is the acceleration during this time? So what do we know? We know initial velocity u is 15 meters per second. The final velocity v will be 0 meters per second. As the displacement is 50 meters, we want to find out a. So the third equation will work. V squared is equal to u squared plus 2as. 0 squared is equal to 15 squared plus 2 times a times 50. 0 is equal to 225 plus 100a. Minus 225 is equal to 100a. To get a, we divide both sides by 100, and a will be equal to negative 2.25 meters per second squared. Final example. A car starts from rest and accelerates at 2.5 meters per second squared. What will be its velocity after 10 seconds and how far will it have traveled? So what do we know? We know initial velocity u is 0 meters per second because it is starting from rest. Final velocity v we don't know. Acceleration is 2.5 meters per second squared. Time t is 10 seconds. Displacement s we don't know. First, let us find v. The first equation will do. V is equal to u plus at. This is equal to 0 plus 2.5 times 10, giving us 25 meters per second. Now we can find s using the second equation. S is equal to ut plus a half at squared. That will be 0 times 10 plus a half times 2.5 times 10 squared. That gives us 125 meters. Now, these three equations apply for bodies moving horizontally. But this is not the only kind of linear motion. A body moving vertically up or falling freely towards the ground also exhibit linear motion. This is called motion under gravity. We can examine objects that are in free fall, which means they are dropped down from a standstill. Or we can look at objects that have an initial upward velocity called vertical projection. So let's look at this motion under gravity. Let us begin with free fall. Now in Form 1, we said that all objects near the surface of the earth experience a force of attraction towards the center of the earth called the gravitational force. And because of this force, these objects tend to accelerate towards the center of the earth. This is called acceleration of free fall due to gravity, denoted by g, and is approximately 9.8 meters per second squared. True free fall can only occur in a vacuum, but if we ignore air resistance, all objects fall with this constant acceleration of 9.8 meters per second squared. Now, because free fall exhibits constant acceleration, then the equations of linear motion apply to this kind of motion. The only difference is that A is replaced by G, and G is always known, 9.8 meters per second squared. So the three equations become, the first one, V is equal to U plus GT. The second one, S is equal to UT plus a half GT squared. And the third one, V squared is equal to U squared plus 2GS. So if a stone is dropped from a cliff 100 meters high, its velocity will increase uniformly from a minimum u, usually 0 meters per second, to a maximum value v just before hitting the ground. So the graph of velocity against time is an inclined straight line through the origin. The gradient of the graph is constant and is the acceleration due to gravity, g. The graph of displacement against time is an upward curve like this. The gradient of the tangent at a point gives the instantaneous velocity at that point. So, in the example of a rock dropped from a height of 100 meters, how long does it take to hit the ground, and what will its velocity be as it hits the ground? As usual, we gather what we know. It's a free fall. So u is 0 meters per second. We do not know v and we do not know t. G we are told to take 10 meters per second squared, and s is the height of the cliff, 100 meters. Let us begin by finding t. From s is equal to ut plus a half gt squared. 100 will be equal to 0 times t plus a half times 10 times t squared. By 2 1 by 2 5. So 100 is equal to 5 t squared. we divide both sides by 5. We divide both sides by 5 and we have 20 is equal to t squared, which means t is equal to 4.47 seconds. Now let us find the final velocity v. We already have t. So from the first equation, v is equal to u plus gt. V will be equal to 0 plus 10 times 4.47, giving us 44.7 meters per second. So that now we move to vertical projection. Now, when an object is projected vertically upwards, the force of gravity acts against such motion, and therefore the body undergoes uniform deceleration of a similar magnitude as g, but opposite in direction. That is negative 9.8 meters per second squared. The body therefore slows down, comes to a brief rest, and then starts falling with increasing velocity or uniform acceleration. So, if we assign the upward as negative, the equations of motion for a vertically projected object become: the first one, v is equal to u minus gt. The second one, s is equal to ut minus a half gt squared. And the third one, v squared is equal to u squared minus 2gs. So graphically, the velocity decreases over time until it comes to 0, and then starts increasing in the opposite direction. For displacement, the height increases up to a maximum and then starts decreasing up to 0. Overall displacement is 0 for a vertical projection. Now, these three equations are very important in deriving expressions for 4 components. The first one is the maximum height. Maximum height h maximum is attained when the final velocity v is 0. From v squared is equal to u squared minus 2gs, we shall have 0 is equal to u squared minus 2gh maximum. Therefore, 2gh maximum is equal to u squared, and therefore h maximum is equal to u squared over 2g. The second component is the time taken to reach this maximum height. At maximum height, the final velocity v is equal to 0. From equation 1, we shall have 0 is equal to u minus gt, meaning that t is equal to u over g. Thirdly is the time of flight. This is the time taken for the body to fall to its initial position. At the end of the flight, displacement is equal to 0. From equation 2, 0 will be equal to ut plus a half gt squared. If we multiply both sides by 2, we shall have 0 is equal to 2ut plus gt squared. If we rearrange, we shall have gt squared minus 2ut is equal to 0. Factorizing the left-hand side, t into gt minus 2u is equal to 0. And that means t is equal to 0, or gt minus 2u is equal to 0. So that gt is equal to 2u, dividing both sides by g, t will be equal to 2u over g. T is equal to 0 corresponds to the start of the projection, while t is equal to 2u over g is the time of flight. And finally, the velocity before hitting the ground, or the return velocity. At the instant the object hits the ground, the total displacement is equal to 0. So v squared is equal to u squared minus 2gs, becomes v squared is equal to u squared, meaning that v is equal to u. It means the object hits the ground at the same velocity it was launched, only in the opposite direction. Let's take an example. A marble is projected vertically upwards with an initial velocity of 35 meters per second. Calculate A, maximum height reached; B, the time taken to reach this maximum height; C, the time of flight; and D, the velocity with which it hits the ground. We start with A. Maximum height is given by u squared over 2g, that is 35 squared over 2 times 10, giving us 61.25 meters. B, the time taken to reach maximum height. This is given by t is equal to u over g, 35 over 10, giving us 3.5 seconds. C, the time of flight. T is equal to 2u over g. 2 times 35 over 10 gives us 7 seconds. D, the return velocity. The return velocity is equal to the launching velocity, so we have 35 meters per second. Next, let's talk about projectile motion. Now, we know the kinematic equations for describing the motion of an object moving horizontally like a car, as well as objects moving vertically like objects falling straight down to the ground. But what about objects that move in both these directions? This type of motion, if it involves object thrown or launched into the air, can be referred to as projectile motion. Imagine a cannonball being fired at some angle from the horizontal. It will travel some distance up in the air before eventually falling back down and hitting the ground some distance away from the cannon. The path followed by a projectile is called a trajectory, and the distance r is called the range. Now, the important thing to understand about these kinds of example is that the horizontal motion and the vertical motion of the cannonball are completely independent of one another. This means we can use separate equations to discuss the motion in each direction. One equation that exclusively corresponds to the x-coordinates or the horizontal motion of the object, and another one that exclusively corresponds to the y-coordinates or the vertical motion of the object. To understand this idea, consider two marbles, one dropped from a particular height and another one that rolls off a surface at the same height with some horizontal velocity. If these begin falling at the same time, they will strike the ground at the same instant because their vertical motion is independent of any horizontal motion. The one with horizontal velocity will cover some distance in the horizontal or x direction, but it will fall downwards at the same rate as the one that falls straight down. And so they will have identical airtime. For example, let us throw a rock at an upward angle of 30 degrees off the horizontal from the edge of a 100-meter cliff and with an initial velocity of 8.5 meters per second. How long will it take the rock to strike the ground? And how far away from the foot of the cliff will it hit the ground? Let us first distinguish between the vertical and the horizontal motions. The time of flight only depends on the vertical motion, no matter what the horizontal velocity is. The range depends only on the horizontal velocity and the time it spends in the air. And the velocity at any moment can also be split into components. The horizontal velocity will be the same at every moment in the trajectory as long as we ignore air resistance. but the vertical velocity will be greatest at the beginning of the motion, but it will decrease gradually until it reaches zero at maximum height, and then become increasingly negative until it hits the ground. We know we can use these equations to find the vertical and the horizontal motion. But you see, the launching velocity, 8.5 meters per second, is neither vertical nor horizontal. It is diagonal. So we need to find the vertical and horizontal components of the initial velocity vector. So if you imagine that we have a right angle triangle and 8.5 meters per second is the hypotenuse, the horizontal velocity Vx will be the adjacent side and the vertical velocity Vy will be the opposite side. Then we apply trigonometry just like we do with length. Cos theta is equal to adjacent over hypotenuse. So cos 30 degrees will be equal to Vx over 8.5, meaning that Vx is equal to 8.5 times cos 30 degrees, and that gives us 7.36 meters per second. How about Vy? Sin theta is equal to opposite over hypotenuse. So sin 30 degrees is equal to Vy over 8.5, meaning that Vy is equal to 8.5 times sin 30 degrees, and that gives us 4.25 meters per second. These two velocities are completely independent of one another, meaning that a rock that was thrown up with an initial velocity of 4.25 meters per second will land on the ground at precisely the same time as the one thrown at 8.5 meters per second at an angle of 30 degrees. That means if we want to find out the time of flight, this is no different than a problem with only vertical motion, provided that we are aware that we are dealing only with the vertical motion. Let's take an example. A cannonball is launched from the ground at an angle of 45 degrees with an initial velocity of 120 meters per second. Calculate A, the maximum height reached, the time it took to reach the maximum height, the time of flight, the distance from the launching point to where it hit the ground, and the velocity with which it hits the ground. So, this is how the motion looks like. Let us first calculate the vertical and horizontal components of the initial velocity. Vx is equal to 120 times cos 45, and that gives us 84.85 meters per second. And Vy will be equal to 120 times sin 45 degrees, again giving us 84.85 meters per second. Now we can solve the questions. The first one, H maximum has all to do with the vertical motion. This is given by u squared over 2g, that is 84.85 squared over 2 times 10, giving us 359.98 meters. B, the time it takes to achieve the maximum height, is given by u over g, and that is equal to 84.85 over 10, giving us 8.485 seconds. C is the time of flight, and this is given by t is equal to 2u over g. 2 times 84.85 over 10 gives us 16.97 seconds. Range, this has all to do with the horizontal motion, ignoring air resistance. Displacement s is equal to velocity times time. 84.85 meters per second times 16.97 seconds. How about the velocity with which it strikes the ground? Now it is important to note that the ball hits the ground also at an angle. As it hits the ground, it has a vertical velocity as well as a horizontal velocity. So let's work out the net velocity. we need to find Vy. Vx is equal to 84.85 meters per second. That one we already know. Now we need to find Vy. This has to do with the vertical motion, and we know that V is equal to U. The initial velocity was 84.85 meters per second, which means the final velocity will also be equal to 84.85 meters per second. Now we can use the Pythagoras theorem to find the net velocity. Net velocity squared is equal to 84.85 squared plus 84.85 squared. Net velocity squared will be equal to 14,400. And when we find the square root on both sides, we get 120 meters per second. So it hits the ground with the same velocity it was launched. And so projectile motion is a little more complicated than one-dimensional motion. But if we know how to divide any vector into x and y components, we can analyze a projectile motion as a combination of two types of one-dimensional motion. Now try this example on your own. Finally, we look at determining the acceleration due to gravity using a pendulum. We take a pendulum tied to a string and hanging from a clamp. The string should be completely inelastic. We measure the length of the string starting from the top to the middle of the bob. Then we displace the small bulb from equilibrium position and let it oscillate. We switch on the stopwatch and measure the time taken for 20 oscillations. Period T is equal to time for 20 oscillations divided by 20. In our case, it will be 28.4 divided by 20, giving us 1.42 seconds. The time period of oscillation depends on the length of the string L and the acceleration due to gravity, G. T is equal to 2 pi times the square root of L over G, meaning that G is equal to 4 pi squared times L over T squared. In our case, this will be 4 pi squared times 0.5 over 1.42 squared. That gives us 9.78 meters per second squared. An alternative method is to repeat the experiment for various values of L and record the results in a table like this one. Then from the expression T is equal to 2 pi times the square root of L over G, when we square both sides, we shall have T squared is equal to 4 pi squared times L over G. We calculate the corresponding values of T squared and plot the graph of T squared against L. The graph is a straight line whose gradient is 4 pi squared over G. It therefore means G is equal to 4 pi squared over the gradient.